Newton's first law of motion tells us that an object will not change its velocity unless it's acted on by an unbalanced force, or a non-zero net force. This means that an object that's at rest will remain at rest, and an object that is in motion will continue in motion with the same speed in the same direction unless it's acted on by an unbalanced force. The second law of motion, commonly referred to as the law of acceleration, tells us what happens to an object if we have a net force on it. If we have a net force on an object, it will accelerate. The second law of motion tells us that a net force causes an object to accelerate in the direction of the net force, and that the acceleration is directly proportional to the net force and inversely proportional to the object's mass. This means that if we put a net force on an object to the right, the object will accelerate to the right. Now, does that mean it's speeding up to the right? Maybe. It depends on whether the object was at rest or in motion when that net force was put on it. If an object is moving to the right and accelerating to the right, then it's speeding up. If the object was at rest and then it starts accelerating to the right, then it is speeding up also. But if the object was moving to the left and accelerating to the right, the velocity and acceleration would have opposite signs, and that means the object is slowing down. So the acceleration is always in the direction of the net force, and that makes the object speed up if it's moving in that same direction. But it makes it slow down if it's moving in the opposite direction. We commonly refer to these force scales as giving us the object's weight whenever we put an object on it. But that's not always the case. This scale does not always read the object's weight. Right now it is. This is a 1 kilogram mass. Its weight is its mass times the acceleration due to gravity, or 1 kilogram times 9.8 meters per second, which is about 9.8 or 10 newtons. So right now the scale does read close to 10 newtons, which is the weight of the object. But if I move this scale up and down, we see the needle on the scale fluctuating. Does that mean that the weight of the object is changing? No, not at all. So the scale doesn't always tell us the weight of the object. What the scale tells us is the amount of force that the scale is pulling up on the weight with. So right now, the scale is pulling up with 9.8 newtons of force. The Earth is pulling down on the weight with 9.8 newtons of force. The Earth's downward pull on the weight is called its acceleration due to gravity. That downward force is called the weight of the object. So the Earth's pull downward on an object is the weight of the object. So Newton's first law of motion says an object at rest is remaining at rest. Therefore, there must be an unbalanced force or no net force on it. So if the Earth is pulling down with 9.8 newtons, the scale is pulling up with 9.8 newtons, those forces are balanced, the object at rest remains at rest. To accelerate the object upward, the second law of motion says we need more up force than we have down force. Well, since the down force is 9.8 newtons, the weight of the object, I have to pull up with more than 9.8 newtons of force to accelerate it upward. When I jerk the scale upward, you'll see the needle move to be greater than 9.8 newtons. So to accelerate it upward, I have to put more up force on the weight than the Earth puts a downward force on it. Now, if I want it to accelerate downward, that means that there's more down force than there is up force. Well, since the down force is 9.8 newtons, the up force would have to show less than 9.8 newtons. So when I quickly lower it from this spot, you'll see the weight needle move to a lower value, showing that there was less force up than there was down. Now, while it's moving at a steady rate up or down, that's a constant velocity, then the scale will read the weight of the object. Because if it's not accelerating, the up force and the down force have to be equal. Suppose you're on an elevator and you bring a scale on the elevator. You're standing on the scale. right when you first start moving upward, the scale would show more than your weight. That's because to accelerate upward, you need more up force than you have down force. So the scale would quickly show more than your weight right when you first start moving upward, but then as you move up at a steady rate, the scale would show your weight because there's no acceleration, so the up force of the scale on your body equals the downward force of the earth on your body, which is your weight. Now, as you slow to a stop coming up to a top floor, you actually feel lighter. Well, the scale would actually show lighter than your weight. If you're moving upward and slowing down, your velocity is up. If you're losing speed, that means your acceleration must be downward, so there's more down force than there is up force. So the up force is the scale reading, so it would show less than your weight. So if you're on a scale in an elevator and you're going to move up, right when you first start moving up, you feel heavier and the scale shows more than your weight. Then as you move up at a steady rate, the scale shows your weight, and then as you go to slow down, the scale shows less than your weight. Now if you're on an top floor and you're going to move downward, when you first start dropping, you feel lighter. Well, you're accelerating downward, so that means the down force is greater than the up force. The up force is the scale, so it would have to show less than your weight. Then as you move downward at a steady rate, the scale would show your true weight. When you slow to a stop, you're moving downward, but slowing down. That means the acceleration has to be upward, which means the net force has to be upward, which means the scale shows more than your weight, and you would feel heavier. So anytime you're on an elevator and you get this sensation that you feel heavier or lighter than normal, that's an example of Newton's second law of motion. The object will accelerate in the direction of the net force, which means the direction of the acceleration, the force in that direction, has to be greater than the force opposite.